Before we look at higher order roots, let's review some things we know about square roots. The square root of 9 is 3, because 3 times 3 is 9, or 3 squared is 9. The important thing to notice here is that there's a relationship between squares and square roots. The square root of a number that's a perfect square is simply the number that's been squared. If you're looking for the square root of a larger number, it may not be as obvious what number has been squared to get that larger number. So you may want to go back to something you've learned before, which is making a factor tree to find the prime factors of that number. The prime factors of 196 are 2 times 2 times 7 times 7. So we have a pair of 2's as factors and a pair of 7's as factors, which makes the square root of 196 14. In other words, 14 squared is 196. So can you see that relationship between squares and square roots? Okay, great. So let's continue and look at higher order roots. Things like cube roots. Cube roots are related to perfect cubes. So if I tell you that 2 cubed is 2 times 2 times 2, or 8, then the cube root of 8 with the cube root of 2 times 2 times 2, and since there are 3 factors of 2 that are the same in 8, then we can say the cube root of 8 is 2. What if we want to know the cube root of 125? Well, let's look at the prime factors of 125. 125 is 5 times 5 times 5, so we have 3 of the same factor of 5, so the cube root of 125 is 5. The cube root of 64? Well, 64 is 2 times 2 times 2 times 2 times 2 times 2, and we have one set of 2's, 2 sets of 2's that are factors, which makes the cube root of 64 2 times 2, which is 4. For all 3 of these examples, you can see the relationship between cube roots and cubes. The cube root of 8 is 2, so 2 cubed is 8. The cube root of 125 is 5, so 5 cubed is 125. And the cube root of 64 is 4, so 4 cubed is 64. How about the fourth root of 16? Well, 16 is 2 times 2 times 2 times 2, and if we're trying to find a fourth root, we're looking for 4 factors that are the same, which we have. We have 4 factors of 2, so the fourth root of 16 is 2. For the fifth root of 243, we can rewrite 243 as 5 factors of 3. And since we have 5 of the same factor, we can say that the fifth root of 3 times 3 times 3 times 3 times 3 is 3. Now we've kept things pretty simple so far. All of the numbers that we've been finding these roots for are perfect powers. If we're looking for a fourth root, we've seen that we have a perfect fourth power underneath the radical. If we're looking for a fifth root, we have a perfect fifth power. That won't always be the case. So let's see what we do when we don't have a perfect power underneath the radical sign. What's the cube root of 40? Well, 40, if we use a factor tree to find its prime factors, is 2 times 2 times 2 times 5. If we're looking for a cube root, we want to find 3 factors that are the same in 40, and we do have 3 factors of 2. But there's only one factor of 5 in 40, so when we rewrite the cube root of 40, that 5 has to remain underneath the radical, in the radicand. So the cube root of 40 is 2 times the cube root of 5. So how can we rewrite the fourth root of 2025? Well, first of all, we'll use a factor tree to find the prime factorization of the number. And we can see that 2025 can be rewritten as 3 times 3 times 3 times 3 times 5 times 5. Since we're looking for a fourth root, we can say that the 4 factors of 3 that are under the radical in the radicand can become a 3 in our rewritten radical. The 2 5's Well, there's only 2 5s, so we don't have 4 factors of 5 under the radical, which means those 2 factors of 5 are going to remain underneath the radical, and we'll go ahead and multiply them together and call them 25. So the fourth root of 2025 is the same thing as 3 times the fourth root of 25. So far we've only looked at radical expressions that have numbers in them. But what if a radical expression has a variable in it? Well, the same principles apply, and let's look at a square root first. The square root of x to the 6th is the square root of x times x times x times x times x times x. And if we're trying to take a square root, we're looking for pairs of x's. So we have 1, 2, 3 pairs of x's, which means the square root of x to the 6th is x to the 3rd power. Rather than writing out all those factors of x, we can go from the beginning to the end by just looking at the powers. If we have 6 factors of x and we're trying to group them into pairs with 2 in each pair, we'll end up with 3 pairs. And those 3 pairs are what we're seeing when we write x to the 3rd power. So if we want to simplify something like the square root of a to the 12th b to the 4th, simply look at the powers. So we have 12 factors of a. We're grouping them into groups of 2 because of the square root. That will leave us with 6 factors of a. And we have 4 factors of b. We'll group them into 2's. So 4 divided by 2 is 2, which leaves us with 2 factors of b. So our simplified answer is a to the 6th b squared. Now here's how that works when we're looking at higher roots. For example, the cube root of x to the 6th, y to the 13th. If we have 6 factors of x and we're trying to group them into groups of 3, 6 divided by 3 is 2, which means we would end up with 2 groups of x, or x squared. The 13 factors of y, when they're grouped into groups of 3, would give us 4 groups and 1 leftover y. So the 4 groups are written as y to the 4th, and then the leftover y represents a y that remains underneath the radical sign. So the cube root of x to the 6th, y to the 13th is x squared, y to the 4th, times the cube root of y. How about the fourth root of 16 x to the 5th, y to the 11th? Well, we know the fourth root of 16 is 2, because 2 times 2 times 2 times 2, or 2 to the 4th, is 16. The x to the 5th is 5 factors of x. If we group those into groups of 4, because this is a fourth root, we would have one group with 1 leftover x. And for the y's, well, we have 11 of those. So if we group those into groups of 4, we would have 2 groups with 3 remaining y's. So the simplified form of the radical is 2xy squared times the fourth root of xy cubed. So now you see how to deal with any radical expression, as long as you recognize that there's a relationship between the radical and a power, and you think of this as simply finding groups of factors. The simplification isn't all that difficult.